Yeah, so good afternoon, everybody. So, konnichiwa. So today we have two speakers talk, and actually Professor Antti Oulasvirta from Aalto University, Finland. So he will give two talks. If you are interested, you can sit back for the next talk. So this one is, first one is for 1 hour, kind of 45 minutes of talk and then 15 minutes question answering. And next talk will be 30 minutes, so 20 minutes talk and 10 minutes question answering. So mostly we are having some input club, keyboard club, and also the second speaker is from dedicated to that particular talk. And so, okay, let's first introduce him. So he is Antti Oulasvirta from Aalto University. He is an associate professor there, and he graduated from Helsinki Institute, University of Helsinki in computer science in 2006, and then he went to UC Berkeley for having postdoctorate, and then coming back and having a senior researcher in HIIT, so Helsinki Institute of Information Technology, and then went to Saarbrücken, so it's Max Planck Institute of Informatics in Germany, and then came back to Finland, so it's his native place. He has been a profound researcher in HCI and machine learning kind of stuff, also cognitive science. He has been elected for many best paper and honorable mention award for our main conference in HCI's CHI from 2008 to 2018. I think 12, right? Yeah. So without any further detailing, I think we should introduce his talk. So computational design thinking, AI and human-computer interaction. So he will mainly focus on how the connection between AI and HCI. Over to you.
Thanks, Saya. So since we're a pretty small crowd, we can keep it interactive, so you can interrupt me. And thanks for having me here. Just arrived this morning from Narita. Hello's from Helsinki. This is a view from Kauppatori, the market square, in case you've never been there. Also the first picture you get if you Google Helsinki. This is my university. That's a 12-minute subway ride. Some of the buildings don't exist yet. Most of them do. In that one over there, it's part of a computer science and electrical engineering. It's a merger university between technology, business, and arts. And pretty brand new. It's 7 years old now. This is our group. We are consisting of mathematicians, computer scientists, electrical engineers. We have a robotics student, a designer, HCS students, cognitive scientists. A pretty diverse group. And not all of them are permanent members. Many of them are summer interns. I'm going to talk about 4 things that we do in our group. Here's a really brief overview of what we do. We use computational methods for adapting and generating user interfaces. Things like automatically enhancing or adapting interfaces. Let's say for the human perceptual system, what we have here, we can get something like this optimized with the human vision. Inferring what people want or what kind of behavioral properties they have or cognitive properties and personalizing interfaces based on that. Generating very complex interfaces that can have up to hundreds of functionalities and the interfaces for them. And then also using machine learning to have better and better simulations of what people do. So these are the 4 areas that I'm going to talk about. To give a little bit of background, to introduce to some of the key players in this area. This is the area called human-computer interaction. How many of you actually follow that or heard about it? Or HCI? No? Okay, good. So I'm going to start with basics. We are using user interfaces all the time. We actually struggle with this very old user interface here, just to get this presentation running. There's user interface everywhere, and in your pen. That's an interface. And the question is, how should they work? How should we design them? What are the principles of that make them good versus bad? And most of the interfaces that we have are one-shot designs. Somebody designs them and they are like that. Maybe you can have settings, you can tune them, but they're more or less like that. They don't have any intellectual capabilities per se to adapt to who you are or what you want. The other actor here is the design practice. So if you think about how those interfaces are designed, that's a multi-billion-dollar business. If you think about how much Apple, Google, Facebook invest into design and innovation of interfaces, that's super important. It's a big profession as well, both interaction designer, interface developer, and so on. Most of this work is manual. Somebody has an idea, implements that, studies it, evaluates it, goes back. And it's very different from, as a profession, from, let's say, civil engineering. Think about how big bridges are built or houses. You would not like them to be built using those methods that those people use, right? Because they have no guarantee for what they do. Okay? So we'd like to change the profession of interaction design to be more systematic, driven by first principles, driven by theories and models. The third actor here is the AI boogeyman. There are many discussions about what can be automated. Here's one from Harvard Business Review. Here's just the level of automation going up and then hourly wage. And if you look at some of these bots, designers are somewhere between 5 and 15%. So that's the estimate of some of the business gurus of how much will be automated. However, things like these are not based on anything. They're just based on hunch, basically. So they are based on analysis of what this design consists of, what interaction consists of, or what AI is capable of. So now that I mentioned AI, of course, you well know the deep learning breakthroughs that started roughly 2014, and now are witnessing a little bit of backlash, and saying that AI winter is well on its way is not helpful at all for our business. We like to understand what can we make out of AI and what form of AI would be useful for us. And you can see, I'm going to show a lot of applications of AI, or let's say rather machine learning, not maybe as much deep learning as let's say Bayesian approaches. So the question is, well, how can we constructively involve AI in human-computer interaction as opposed to seeing them as automating and being this boogeyman? Designers also have been very interested in what can be automated and what's the role of AI. Here's a classic piece from 1998, but the work predates that all the way to the 80s. And it's by Nigel Cross, who's one of the forefathers of intellectual research on design. He established the field of design research. And he was looking at this for a long time, and this is a keynote that he gave. And he was saying that design has all these qualities that AI of that day, that was mainly based on logic and reasoning, logical reasoning, does not have. But once you engage in the business of trying to formalize and algorithmically solve design problems, you actually come to understand about the natural intelligence of design. And this would be very beneficial for design as opposed to trying to automate that. Okay, in the rest of the talk I'm going to go through three claims relating to all of these things. So first of all, I'm going to show that what could be called weak AI. So it's task-specific AIs, artificial intelligence for certain design tasks and interactive tasks, is already reality and is already here in some form. So I'm going to show that thanks to that, then we actually can do much better theorizing and modeling in human-computer interaction. And then I'm going to discuss the point of, is strong AI possible in human-computer interaction design? I'm going to start from a little bit of basics, because this talk is entitled Computational Design Thinking. Well, what is computational thinking? Computational thinking, this infographics from BBC, consists of decomposition of a complex problem, abstraction, being able to see the abstract form of the problem from the instance, pattern recognition, and algorithmic solution of these problems. This is computational thinking. You can think about, for example, how would you instruct a robot to pick up some milk from a fridge. So we decompose problems, we abstract problems, and we construct algorithms for solving them. This is computational thinking. So when you go to computational interaction, computational design, then what does it mean? It means that we apply this notion of computational thinking to interaction between a computer and a human. What it more precisely means, and the rest of the talk builds on this, we have a model. That model can be a mathematical model, like a rule system, or it can be a deep learning system, or whatnot. But there's some mathematics that is basically a model that is tying together some data coming from the user or designer, that is then inferred as the parameters of the model, and that is then used to optimize or change the design, to speculate, well, what would happen if I change the design to be like that. So all of computational design involves some sort of model, some way of updating the model from human data, and then some way of synthesizing or adapting designs. So this is already a radical departure from the regular way that we do human-computer interaction, which is based on innovation and evaluation, because we already admit that we have to have some sort of mathematical modeling in the center of what we do. Well, what are those mathematical formalisms? Just this year we published a book doing an overview of I would say almost all of them, going from logic to agents to optimization, probability, and so on. I'm going to touch on some of these, and if you're interested in them, you can look at that book from Oxford University Press. Summarizing over all of these, what are some benefits that we're looking at? We're trying to look at design and interaction that is scalable, because once you get the algorithm right, you can reproduce that in mass, unlike in manual design. We have analysis, meaning that we can make testable, rigorous descriptions of interaction and work directly on them. We can improve designs. We can support designers and adapt interfaces automatically and customize. I'm going to show examples of all of this. Finally, before I start a little bit more about what we do, just a little bit of historical context. AI has consisted of many waves, just like human-computer interaction as well. You could say that cybernetics, which actually created many of the foundations that we should be referring to in our field, embedded already before the Second World War, is fully forgotten. Then we had logic, cognitive models, machine learning 1, machine learning 2. So we're going from formal methods and formal reasoning to cognitive models in the 1990s, and then let's say support vector machine, for example, was a popular model in this era, and then now we're looking at like Bayesian optimization, deep learning, and so on in the second era. And I'm combining ideas and methodology for many of these. One main point being that pattern recognition per se, sort of the pure quality that you get from deep learning is alone not sufficient for what we need. To be more precise, we need something else, because we need control, we need explainability. And that's, I think there was a recent summary of main AI methodologies, dividing into planning, optimization, model-free learning, model-based learning. And what I'm going to show is combining many of these into what could be called white box approach. White box in the sense that we can peek under the hood, we find theoretically plausible, theoretically justified models that actually may come from psychology or even biomechanics, that we parameterize using machine learning, and that we then using machine learning optimization to do better designs. And this makes this approach is controllable and explainable, also less data dependent within so many observations. So lots of good qualities come if you're willing to go this hard route of white box AI. So I'm going to talk a little bit about optimization first. And this is something that I've been working on since 2011. This is, though, not my idea. August Dvorak, who designed the Dvorak simplified keyboard, he's one of the pioneers. He wrote this book called Typewriting Behavior. And he had like 15 different ergonomics and psychological principles or laws or effects that he found, that he then used to manually redesign the layout. So his work is pioneering. Many others had also proposed the same idea of using psychological models and theories directly or systematically or algorithmically even to design better interfaces. All of those eventually boil down to a very simple idea, and this is actually quite enlightening if you never, let's say if you have basic computer science, then you understand that I can do optimization. So all you need to have is some sort of method that goes through possible candidate designs, let's call that capital E, tries to find the one that maximizes some goodness function G and under some task instance specific parameters theta. So all of the examples that I showed fall within this basic notion. So there's a predefined design space, predefined goodness function. The theta may change based on the task instance that you have. I'm going to show one of the core areas of work, which is keyboard layout optimization. There's work going all the way to the 70s, from the Hebrew keyboard to Germany, to the US. This is one example from 2000 where they looked at stylus, PDS and stylus, and a virtual keyboard that you have to optimize. Basically, the question is that how would you place letters like this onto pre-given key slots like that? And there's of course n factorial number of ways of doing that, because where n is the number of layers. And then you have to formulate in the optimizer some objective function. In this case, that would be to try to minimize the finger travel time weighted by the probability of those letter transitions occurring in that. So we can show that, for example, E and H would be very common, whereas Z and X would be less common. And then you weigh that, use that as a weight to weigh some model of how quickly people can move their finger, for example. In this case, that's a model called Fick's law, and it's very simple. Basically, tells gives the moment time as a function of distance and width of the target of the moment, and then there are two empirical parameters. Then you can throw it into a black box method like simulated annealing, and you can get a result. This was the standard paradigm I'm building on as well. Right? I'm basically having similar. I formulate a task, I have an objective function, and I throw it in an optimizer. Following this approach, we can actually generate quite interesting interfaces already. Well, way further than keyboard. Nevertheless, I'm going to show you one keyboard example because I'm particularly proud of this. We're working with the French standardization organization called AFNOR, and this is coming out 15th of September, so next month. We have redesigned the special character mapping using an optimizer, taking into account the performance mode of special character, so like Control Shift and so on, right? These characters. We taking into account performance, learnability, ergonomics, and familiarity. And we formulated those mathematically and solve a problem using a method called integer programming of these cardinalities, an immense problem. So there's 10 to the power of 80 atoms in the universe, and this is way harder problem than that. And you can solve it efficiently using modern optimization methods. So now this is going to be part of the French keyboard C. Now, following similar ideas of what is called an assignment problem, we can start formulating more complex problems like menu design. You can design a menu following similar ideas. Now you have to assign commands to groups and tabs and order them. And we found a new way of doing that, combining two objectives, the speed of selection and associations between selection, and then we formulated another one using a theory from psychology called origin theory. That's basically the theory of how people navigate when they try to find a particular target. Now, we expressed that mathematically, and then we rigorously compared that in a controlled user study against commercial baseline designs like Adobe, Firefox, and those. And these optimized menus were 26% faster to use. So you can increase the number of functions that you can offer by using this method. All you need to give is a list of frequencies of commands and list of pairwise associations for those commands that have it, and then the optimizer does the rest. This is another piece of work that I'm quite proud of. There's a possibility of using perceptual models, pretty basic perceptual models of human vision, to try take a default clock like this, and it wouldn't show any of the structure, and automatically produce something where the human vision can much better see the structure. And underneath this optimization are objective functions like addressing contrast perception, brightness perception, unit formation, when we see units that form a whole together. Actually, there were altogether 10 objectives, so it turned out to be more complex than we hoped. Anyway, if you take those 10 into account, you get something like that. Now here's a gallery of some of the what our group has done and what other groups have done. We can do layouts, we can do web pages, and visualizations, we can do gestures, menus, and then widget control. So pretty many aspects of graphical interfaces can be addressed with this approach. They are limited in the sense that if you start putting them all together, they would break down in the sense that how would you then control, you're not able to produce, like, people often ask me, well, can you produce the next Microsoft Word? Well, probably not, but I can optimize the toolbar, I can optimize the menu, I can optimize some commands that you have. We're also looking at game-related performance. This is one example that we published this year and 2 years back. We have models of how accurately people can respond or select a target in time. And so you're shooting an enemy, for example, or jumping this Flappy Bird character. And as a function of how quickly the Flappy Bird goes, how much is the preview window for your perceptual system, how wide is the pillar that you have and the gap. Then you can predict pretty accurately whether you're going to die or not. Then you can use that as a principle of game level design. Here's another one where we did skim reading. So if you have a long document, it'd be really hard to see anything from it.
Spotlights to enhance skim reading performance of long documents. The technique highlights headings and figures from the document by superimposing them on the
So it optimizes those overlays based on an attentional model that's going to say how much time do you have to dedicate per object and how many objects can you simultaneously process. Using this very simple attentional rule. And it significantly improves your ability to skim really quickly, let's say master's thesis or textbooks or whatever you're having to do. Here's another one I just included based on our discussion this morning. It's about mapping letters and letter pairs to the piano keyboard using Beethoven and English as the basic statistics. So doing playable English music for a pianist. So a pianist, after 100 hours of training, can then type 80 to 100 words per minute. This is showing a completely different form factor. Now we can solve using optimization how to do that. Immense number of hours, went to practice this, right? But to us, it's just proof of concept. We don't believe that people would adopt this, right? This is more like a show of force. Okay, so I'm going to take a one step back and look at, well, what does this optimization mean? How is it really done? So in optimization, you have a space of tentative designs that's called a capital D design space. Somewhere there is a set of basic designs that you're interested in. You have to have a process of searching, that's the algorithm, that's the optimization method, and you have to have a solver that does that. The solver can be anything. Luckily, there are very, very good methods, black box methods and exact methods for that these days. You have to formulate the objective function, what constitutes a good design in this case. Then you have to parameterize the task instance that, okay, this time I'm designing for English language or Japanese language, and these are the characteristics of the case. And those can come from designer or user. If you talk about this example, we're talking about interactive tool that interacts with the designer so that the designer can specify this. If you talk about this route, you talk about inference. I'm going to talk about that later. So this is the way I teach computational design, that there's this stool with 3 legs. At the top of the stool, there's a model of interaction that's doing some sort of prediction about linking design and outcomes in interaction. And then there's a process of optimization that goes through designs. There must be some way of inferring the parameters from data, and there must be some way of doing prediction, meaning that it can speculate, well, what if I change the menu like this, what will be the consequences to our users? I'm going to talk about all these legs in the rest of the talk. So optimization is about the process of searching for desirable designs algorithmically. Most of you must know optimization, that here's an optimization landscape. You have 2 variables. For example, you need to design the x and y coordinates of a button. And the height of the landscape here shows how good the objective function could predict that to be. So in a way, what the optimization is doing is trying to find, for example, the highest peaks. Well, in this case, there would be quite many of them. And all of these are trying to find a good compromise between how widely you explore versus when you drill down or exploit. And what makes interface design always unique to us, we have multiple user groups and multiple design objectives and multiple characteristics that we have to take into account at the same time. For example, when we designed the French keyboard, we have to take into account how they type social media, like how they tweet, which is very different French language than the other ones. We need to take into account formal French language that they write in newspapers and so on. We also need to take 4 objectives into account. Very, very large design spaces that are very hard for humans, also hard for algorithms. For example, if you have a menu that you need to organize hierarchically, it only has 50 commands. You have this many, 10 to the power 158 ways to organize it into hierarchy. But that's why humans, when they design, they easily fixate with a known menu design, and start just modifying from that. And this is exactly where algorithms can help designers. One outcome from this is that design is most of the cases, is the best. It's the process of finding the least worst compromise or the best compromise. Least worst in the sense that it's always compromising somebody or some objective or whatever. But here's an example from web page optimization. You have, let's say, 5 different objectives, and if you optimize for any one of them individually, they don't make any sense. If you take all of them in some carefully weighted balance, and you start getting results that make some sense. What's also nice about it, you can use it as a toolbox for problem solving. You can find what is called the target front, that are the best trade-offs between competing objectives. You can do robust optimization, meaning that you find the best, the design that is the most robust to changes in assumptions. For example, if your users change or if your initial values that you gave to the optimizer are questionable, you can do that. You can do exploratory optimization. You can ask the optimizer to explore widely diverse design ideas. And in local optimization, which is where you take an existing product or design, you just ask, well, if I was to make just one change to that, what should that be? So you can use it, once you've done it, you can use it like this for anything. For example, you can use it interactively. We have published a few tools where designers can, this is from Kai 2016, this is a demo where this is a regular workspace for designing wireframe designs. And then the optimizer is making suggestions based on its models and optimizer. Basically saying that if you take this layout, it's going to be better than this existing one in usability, but worse in aesthetics. Right? So it's giving some suggestions on why it's making these things. You can also fine-tune colors or particular elements using these widgets on the right. And we're working now with Huawei to actually put this into practice in their actual design tools. Here's another one that we're working with. This is way harder problem. This is called mood board design. This is something that interior designers, architects, graphic designers use. And we have what is called cooperative bandit system that is trying to recognize it's trying to have a model of the mood board, and then it's trying to recognize whether the user is exploiting, and then it's making suggestions on the right that the designer can take. And so you can basically start from nothing and let the AI construct a full mood board for you, or you can at will you can ask for guidance. So now we're in the process of testing that. So that was the first leg, that was the optimization leg. So the second really important part that has driven us away from deep learning and toward like mathematical models, simulation models, is prediction. Because we need to be able to say that, okay, if I take this design choice, then this is the consequence in terms of performance or learnability or whatever is important. And whereas in regular areas of optimization operations research, you typically refer to, let's say, physical models or something like that. This is, the topic of decades of work. You cannot take physics and predict how people behave. That's not the model of what they do. So you need to resort to behavioral content models to achieve exactly that. Of models, you can even have if-then rules. You can have regression models or simulation models. Simulation models, of course, the downside is that then you have very expensive evaluation time, so that limits the design space that you can go to. Here's a model of the menu selection performance. It's just a regression system, so you have regressions that can predict, for example, the time that it takes for a user to find an item in a menu. So once you've given that, now you can give it to an optimizer. And actually, this menu model accounts for 5 factors in menu design. Where the item is, how long is the menu, what type is the menu, how many times you already seen that, and some other one. And in a way that has been empirically verified. Right? So it makes better predictions on usability than a human designer, because no human designer can internalize a model like that. Now, one thing that we observed is that in opposing the idea that we try to fully model a user behavior, what we actually do is we start from optimal behavior, and then we start slicing away using bounds. So we say that assuming that users have peripheral vision that is limited, or assuming that users cannot move their fingers infinitely fast, then they must be below this barrier, right? So we start slicing their performance envelope using bounds. These bounds are coming again from psychology, from the sciences. They can be about how quickly people can select targets, but they can also be about color harmony. We can give a bound that if you put the colors like this, then this is the best possible color harmony that people can achieve or perceive there. But this is the best possible reading time if you're laying out text, or this is the working memory bound. People will fail using your interface if you don't take this bound. So we start adding these bounds and we slice away a better and better, we sort of sandwich better and better estimate of user performance. Now what we've been doing in that endeavor is we've been using machine learning for predicting how people adapt their behavior. So there's a very big boom right now in AI in reinforcement learning. And that comes, of course, from Pavlov, right, all the way to the Russian psychologist studying rats. And now, none of those mechanisms of self-adaptation were included in the old school cognitive models that you would see having modules that have inputs and outputs. Put something in and outputs come out. But it would not have a self-organizing principle. Now what we do is we can sort of light these models up by including machine learning in them. So what we basically do, we can treat each one of them giving some bound, temporal bound or capacity bound or whatever, and then we add here machine learning, especially reinforcement learning, to make the estimate of how could a person best utilize, best behave, assuming these bounds and the task that they do. And we're trying to give an intuition. So let's illustrate it like this. So let's say I'm going to show you an interface, and all you need to do is to find the link that leads you to politics news. Okay? So here's the page. So where is it? Oh, it's over here. I know because I've seen this already, and that's the trick. I actually used my memory, right? Unlike you guys. So we have different resources. I have different resources as you have. You can, for example, you can scan with some systematic approach, or you can try to look at the salient regions that you see with the peripheral vision. You can try to recruit your memory, but that's going to be slower. And what machine learning is giving us is an idea of how we're going to solve this problem, given the resources that we have and given the paths that we have. And this is an emerging field of research that is in a big boom now at the intersection of cognitive sciences and AI. This is one very nice way of summarizing it, coming from a textbook exposition of the topic. You have an environment. This is the task. This is the page that you're looking at. It has particular locations and colors and so on. Then you have mechanisms. These are the things that are causing you, for example, For example, you have to move your eyes. You have blurred peripheral vision. You have slow memory. And then you have utilities. There are certain rewards that you want to attain. For example, you want to get to the politics page. Now, all of these can be formally expressed in reinforcement learning. And then you can let the reinforcement learner learn the strategy that users might use in this case, in the best case. And across our studies, we found that this is often a good approximation of user behavior. So how can you obtain that? You can have policy learning, utility learning, reinforcement learning, Bayesian brain. Let me give you one example. For example, if you're looking for a particular element here, let's say Excel, that's going to be easy because if you knew that it's green, it's the only green icon here. But if you're looking for that one, it will be way harder, and you have to have more exhaustive scanning of that. Right? How can we predict which strategy will we use? So here you see in action what I just described. There are some bounds, and then there's a controller that learns. Okay, so the bounds in this case would be visual short-term memory, long-term memory, feature guidance, like what kind of features do you see on the page, and of course the resources, which is that you move your eyes. And the controller would like to learn the best policy of using these resources when solving this problem. This is where we've been using utility learning, for example. Now what you can do is you can simulate a novice user not having a big memory of the page, and then you can simulate an expert user. I'm going to skip this one, which is the Bayesian brain hypothesis, but this is also a big thing in neurosciences right now. The idea is that people's brain operate in a somewhat Bayesian statistic fashion, meaning that they have a model, and they have data, which is the input data from the sensors, and then they construe or infer that data in the light of the prior that they have. And this has been quite influential and cutting across areas like psychosis, perception, and remote control. I'm going to show in the next talk the key keyboard meetup science talk, how this works in practice. So the last leg of the stool, so we've been talking about optimization and prediction, is inference. How do you get from data to a model parameter, to model parameters? And this is in a way a key question in human-computer interaction in general. So you have lots of observations about people, how they click, what they do. But the question is, well, why did they do that, and what did they actually do? So let's say that let's go back to this example. Let's say that somebody clicked over there. Well, what does it mean? Maybe it was an error. Maybe the person wants to click here and open this. Maybe the person has never seen that before, but is exploring and just trying out what happens. So even from one click, not to mention lots and lots of clicks and observations, it's hard to say what actually happened. So this area is called inverse modeling. Normally in psychology and in computer sciences, we talk about forward modeling. We have a simulated model, and then we go with some parametric assumptions, we go to user behavior. Let's say that this box is all possible behaviors, and every particular behavior is just one dot. Now, in forward modeling, you go from a simulator to predict something and see how the model behaves. In inverse modeling, you try to find the exact parameter setting for that model. All models have some parameters that produces behavior that is very close to the real user's behavior. That's called inverse modeling. We've been doing that with Bayesian optimizer. So you can take those models that I discussed, you can put them into this Bayesian optimizer and tries to find the best parameters, theta, that then best fit that user. So we're actually solving pretty hard problems. So the problem is, I have to actually go to the end to show that. You're actually just given click times, nothing else on a menu or web page. And now many different properties of the human visual system characterize you as a person. And can we make any assumption or any estimate, reliable estimate, from the way you click and the click times about these parameters, and using that model that has been then parameterized, can we produce plots that resemble your behavior? And it turns out that we can get some basic parameters in the visual system about fixation length, saccade length, just from the way you press the menu. What's nice about this Bayesian optimization, unlike many other, let's say, unlike unsystematic approaches that you have, it yields what is called a posterior distribution. So let's say that you have two parameters that you're interested in, some memory parameter and a human visual system parameter, and it gives the space of explanation. It says that, well, this parameter can be here, but then it's most likely the other parameter is over here, right? So we can actually systematically work with the plausibility of your parameters, which is not easy before basic methods. Now I'm going to talk briefly, before I conclude, work that we've been doing also with Cyan here, which is ability-based optimization. So here we combine some of these ideas. So there are many sources of individual differences, starting from anatomical differences, going all the way to cultural differences and whatnot, motoric, perceptual differences and all that. And all of those are, in the end, to us, just parameters in some models. Okay. So people are just parameters. So if you think about entering text, for example, we can produce pretty good predictions of text entry performance with these parameters using a generative model that moves the eyes and moves the finger. So now these parameters are describing also individual differences. They would describe, for example, how much tremor you might have, or what your working memory capacity can be. And now we can change them. We can change them according to you or according to any special group. Here's an example of, this is a workbench simulation that we're simulating text entry performance here on the right. So somebody's writing in Finnish language. I'm sorry, this is English language. And the red dot is the eye, and the red dot is the finger. Sorry, the red dot is the eye, and the yellow dot is the finger. And now, depending on the parameter settings, it's going to find different strategies, because the machine learning algorithms have to find, well, what's the best way of solving this text entry problem using the resources that I have. And now what you can do is you can then start asking them, what if I have fundamentally different capabilities? Let's say that this is the regular design that you use on a regular device, and the optimizer found that for people who have tremor, it actually makes sense to combine some of the letters or group them into keys. course, the consequence is that then while you can hit the keys, then of course that's not unambiguously describing the word. So then you have to have a word prediction list like that. And what it showed, the simulation, is that then you can actually go down from an error rate of like 50 or 60% for tremor users to like closer to like 4 or 3%, while not compromising words per minute. So at least then tremor patients can type at all. An extension of this is trying to put all of this together. You have the inference part, the prediction part, and the optimization part. If you put all of them together into one place, then that's called self-optimizing design. It can have autonomous inference. Here's one example of a menu, self-optimizing menu. So this is speeded up. That basically it records what people are clicking, makes an inference about what people are interested in, uses a model to predict that if I change the menu like this would be the cost. And then over time it starts adapting. It highlights and reorganizes the menu for you. Here's another one. So we can follow your web browser history. So we have a web browser plugin. And it follows that, okay, this is the history that you've seen in this domain. Let's say that this is a particular domain of e-commerce. And we parameterize the visual search model to your experience. We know that you've seen logins over here and emails over there. And now what we can do is that before you have actually seen a page, we ask from the visual search model, modeling you, that where would you look if you were to look for email? And then we use that as the objective function. We try to make this familiar as possible. And then we make it like this. And we found that it's 25% faster, 25% less fixations than in the non-optimized layout. And that's taken into account what your history is. So to conclude the very long talk, here are some discussion points that I want to raise up. So we started with this discussion about, well, what can be automated. Now I think we're closer to 0 to 5% automation level in design than 100% or 50%. We can delegate certain tasks. We can use optimizers to solve really hard problems like keyboard design or menu design problems. We can use them interactively. We can learn certain basic things from user data and automatically adapt some aspects, but it's far away from replacing designers. So what we can do is we can, I basically listed this, we can embed design knowledge and designers thinking into adaptive interfaces, make them self-organized. We can help analysts and designers in looking at complex behavior, and we can give tools and problem-solving capability that wasn't possible before. When people think about AI, they often think about the strong AI boogeyman. Okay, it's going to automate fully what we do, and I think it's even close there. But I want to make this argument a little bit more involved, and I took a definition of design thinking, and this is a couple of months back. Design thinking is an all-encompassing word about how designers think as they solve design problems. And I listed 5 of them, and then we discussed, well, which one of them are amenable to AI and which not. First of all, design thinking involves the creation of artifacts. Secondly, it's about problem-solving activity. Given a problem, find the best possible solution to that. It's about reasoning and sense-making. So you have complex data, for example, you want to make sense of that. Then it becomes harder. So in this, let's say, pretty canonical definition of design thinking, then reflective practice means that you're constantly, as a human designer, reflecting how well you're doing and how to have a sort of meta level of learning and reflection. And the 5th one, which is even harder, is how do you create meaning? For example, what would be the meaning of a product or a brand to a user? Also, if you think about the process of design thinking, typically it uses imagery, sketching, iteration, and constantly redefining the product. And now I use this traffic light metaphor to give my current views on this. I think I've already shown examples, and other groups have shown examples of being able to solve problems, create artifacts. As simple as they look like menus, they're actually pretty hard to do. They are making less progress in terms of reasoning and sense making. We can get something, we can get intents, we can get people's personal characteristics from data, and we can work with them in design. But I haven't seen very good examples yet, but I think it's moving over there. We are not even close to what could be called reflective practice, where you have linguistic and embodiment aspects of work. Optimization and machine learning, it is working somewhat similar. Of course, it's based on formal algorithmic solution, like imagery and sketching. It is producing candidate ideas and evaluating them, just like humans do, but millions of candidate designs per second. It's very different in that respect. There are two very hard philosophical challenges. Also, read the philosophy behind that. I divided them into two categories. There's the Vinograd and Flores argument from a classic book that they had called Cognition and Intelligence or something like that. And then there's the Dreyfus argument from a classic book called What Computers Can Do. And so basically the first is saying that design is not just about laying elements on a canvas, but it's also about communicating what you mean. I'm just going to give this example of Gmail. Many of the elements that we have here, like how do you divide the widths and how do you put the icons and color choices and all, those we can handle, right? But we cannot handle things like how would you choose a very good label for a command. That's linguistic communication. So that's part of this problem. The other one is this, that then of course the AI doesn't exist in the same world. It has no access to how people would interpret that or start adopting that. But it can help, especially in visual spatial aspects of design. What's very valuable for me as a scientist working in this area, that then actually when we start formulating something like menu interaction, we are also advancing our understanding of what interaction is. And I think that's the most motivating factor for me. I wouldn't be intellectually satisfied if I just had a deep learning black box and then I get something out that I could explain or do anything reasonable that we can. Even if somebody made money out of it, I'm interested in it. Okay, so with that I want to thank you, and if you're interested in, there's a summer school coming up, just actually next week. There's a book, and if there's any takeaway, then that's cool. Thank you.
Thanks. Questions?
Thank you so much. It's very impressive that AI can improve it. Yeah, so I have a question on the future works on this direction. This is very simple censoring of the user behavior, but it may be possible with sometimes the agent styles, the interaction, and finding how user have model and improve the interaction. So I hope your comments about the future direction.
Okay.
This kind of information.
Yes. You mainly refer to more intelligent forms of interaction like chatbots and...
Yes, and also this kind of interaction may be more deeper difference for the user.
Yeah, I haven't gone into chatbots because there's a limited resources that I can have. Obviously, it's already important there, right? And it's doing similar things. It's doing inference, it's doing optimization, it's choosing the dialogues and responses that it should be doing, and it's also learning from the responses that it's getting from the user. So it has many of the same elements, but completely different, let's say, algorithmic problems and modeling problems. I never went to linguistics because and chatbots because it's really requiring its own background. So what I'm saying is similar progress as I shown here is shown there, or even further. Right? So I think that then maybe in the future there could be some sort of convergence where you not only choose what the chatbot is saying, right, but you also choose the way it's presenting its information and the way it's presenting its options.
Yes, but maybe more simple interaction like printing some kind of rights or some kind of interaction still make some kind of inference toward the user behavior. So it's kind of the active learning in the robotics. So so it's kind of not sure maybe utilized in the future.
I didn't yet talk about active learning, but of course the next step after prediction, optimization, and inference would be active learning, because I discussed that there are theta, these are the parameters that are not known that describe the task instance, but then to the extent that there are also variables and structures that affect interaction that are not observable in the model, then you need something like active learning to support what I showed here. I haven't done that, but that's an exciting possibility. The question is, how would you combine them? If you have an active learning component, it has its own model, and how do you combine that with the model approach that I have here? I have some work with robotics people on this topic, but we don't have any results.
Thank you.
Other questions? Please.
Thank you very much for your presentation. As you mentioned, some perspective about the psychology, and as my major is about social psychology, so I'm pretty interested in the question of what do you think would, in your opinion, what would be the desirable relationship between the AI and the human being?
Yeah.
Yeah, and because you are designing this AI, so what do you think, what kind of effects would we have in the near future, since it would be a very good picture for us? But I do think there might be have some negative effects too. So what do you think, what we can do in order to have a better relationship between both of us?
First, I just want to make a general remark that the way I do my research
Okay.
sort of ensures, or let's say that is there's less of a risk that it will sort of get out of hand and become runaway AI, right? Look at, we're doing menus and layouts and stuff like that.
Yes.
But we want to understand exactly what they're doing. So we're not treating this as a data learning problem, data-driven problem where you learn from data, have a big black box model, then it does something complicated that you don't understand. But starting from this white box principle. So just from the starting point, there's more controllability and transparency. But it doesn't mean that, so I cannot tell what's a desirable relationship between human and computer, right? I'm trying to make one type of relationship possible where you can expect an interface to adapt and learn from you, but only a particular subset of those things that are, let's say, quite acceptable. Things like your beliefs or cognitive properties and behavioral tendencies, but nothing about deeper things about, let's say, religion or stuff like that. There's a lot of work already from the 90s on how people perceive computers. There's a classic book by Cliff Nass called The Media Equation.
Yeah, it also in Japan. My boss has done a lot about it.
Okay, yes,
Yeah.
yes. And that made the assumption that people attribute to computers similar qualities as they have in humans, right? I think this has started to break a little bit. I think if you look at discussion about AI, people, especially when it has AI, so the computer of that date didn't have the same AI capabilities we have this date. Now we see more of the demarcation and critical discussion about that question. And I also studied a little bit of social cognition. That's one aspect of, let's say, human-computer relationship that would be interesting to try to, let's say, optimize or learn about and so on. Right? Let's say things like how people infer each other via Facebook. Could you do interfaces that are less, let's say, less susceptible to flaming or other aspects of negative behavior in the internet?
And to form
better relationships. Yes. So I think there's possibility for that. The way it works at the moment, as far as I see that, is that some company or research group comes up with an interface and argues verbally that this is the way it should work. Right? That's good. Then you populate the design space with lots of ideas. But then if you cannot theoretically explain that, then you cannot really control that either.
Yes, thank you for your presentation. You mentioned about eye tracking study before in your slides, and I just want to know that in the current situation, what kind of we can do with the eye tracking data to optimize some kind of learning. I'm kind of learning about MOOCs right now, and what the learning behavior in MOOCs, and what can we take from the eye tracking to the behavior of people in the MOOC for optimizing the the e-learning in this case?
Yeah.
Based on your opinion, thank you.
Yes. It's very hard to go from the way eyes move to education and learning, right? Because there's a very long gap between how we move our eyes and how we should be learning about something. Yet, what you could be able to do is to infer, for example, from the way they look at, let's say, mathematical objects or language objects that you present on the screen, is that what they might believe about it. And this is an area that I really cover too much, but it's called inverse reinforcement learning. You'll be able to learn the utilities, basically the reward functions of learners and what they find important. And then what you can do, you have the model, you can then speculate that what if I change the environment like this, then this is what would happen. I think we're pretty far from that. I think we're best at the moment dealing with like sensory motor, let's say lower level cognitive aspects. But maybe in the future that's possible. What it needs is a theory as a glue. The theory should explain eye movements. It should explain how eye movements are different in different learning conditions. And if we had such a model, then you can learn the parameters of an individual learner and then use it in the optimization step to optimize it. But as far as there is no, as far as I look at educational psychology, typically they don't talk about eye movements. So there's a gap, and you have to somehow fill that gap between learning and eye movement. There's, for example, a theory of ACT-R of John Anderson. Do you know that? ACT-R? That has been very powerful in cognitive tutoring. And that's one example of a model that can do eye movements. And that's exactly the way they actually do that. So they look at mathematical problem solving, try to learn the parameters that describe you as a learner, and then they can choose, for example, in a little bit in a fashion of active learning, what should be the next learning intervention. So that's maybe the best example of work that's already done.
Thank you.
Any other questions? I have sort of questions, but I'm not sure. Maybe the time is running out because it's 4 o'clock and we will start from 1:15. Let's talk it offline. So I would like that interested in kind of like this kind of approach, what we were doing actually, like when we were doing the model-based optimization, so ability-based optimization. I really felt like one point is kind of like we have a different kind of users, right? So we have a novice, intermediate, and expert users. So I really feel might be I have some argument kind of this kind of like whenever you were extracting data from the eye movement or like motor movement, so we found really that if people have clear idea what they are doing, so then it's easier to infer, and the model can more closure to get more fit. But if people don't have any ideas like what actually they're doing, so it's kind of hard. So if you are in a novice area, like people are actually novice, then this kind of approach, kind of like having less efficiency, but like we found it because when we were doing the interactions like a user experiment kind of thing, but might be like I was thinking like how it can be improved later, like to understand, because the novice users usually we actually dealt with the Japanese older people, might be different cultural difference than Western part of the world kind. So it's a kind of like they actually learn slowly what is going on the interface when they are interacting with it, and the time is like changing for different person. Like some people can make it more fun, like out of it, and then make it learn in 15 minutes, 20 minutes. Some people maybe 2 sittings of 1 hour, even don't understand what is going on. Even we explain it before. So it's kind of like it seems like still for those people, this kind of approach, it's still having a little bit lower result kind of thing. So I was like that time thinking like how to cope up with this. Maybe we can discuss.
No, I just want to really briefly say that whenever you do inference, you have to have some model, and with model comes assumptions. Right? And the kinds of assumptions that we do here, for example, in terms of learning, are often based on the optimality assumption. For example, you learn the optimal policy, but you don't learn the way the user does. Right? So what the user achieves in the end might be a good approximation, But the way people learn would be quite different. Often people learn actually much faster than what a model predicts, because they have such different learning styles. So.
Yeah, I was interested, like you did say at one point, like model without model learning, inferencing in the AI, we have a
Model free,
yeah, model free actually. Yeah, now I might be that one I work like to see that how things are going. Might be like I'm not sure, like there could be some mixture kind of like model free and model based. So
I think it's a matter of incorporating more of the systems that people use. So if you take a textbook on neuroscience and open the chapter on memory, you find that people have 8 different memory systems. Now reinforcement learning and the Pavlovian system, that's like one of them. Right? Then you have other ones, semantic and episodic. And there's pretty good progress in actually modeling also those in AI and machine learning. There's more and more NIPS papers every year simulating those. So maybe in the future we can actually get a good hunch on how people do from the very first exposure on.
yeah, when we were doing the same thing, when we were doing literacy about Selvusis model, actually also it's based on one particular way of doing researching. So yeah, it might be different. Thanks. Thank you very much. Again, we can thanks. Maybe we can have a break, like 15 minutes.